Hello everyone, I'm Kiko. Welcome to my Capstone research presentation, Information Preserving Leg Study of Future Spot Price Relationships. I conduct this research as part of my project at the University of Sydney, supervised by Professor Joseph Lizia. This presentation including 7 parts to introduce my work. I'm gonna start with the first one, research background. On this slide, I'd like to give a quick overview of future markets and why we care about the relationship between future and spot price. A future contract is simply a standardized agreement to buy or sell a fixed amount of commodity at a predetermined price on a specific future date. In practice, most hedgers set the future price based on the current spot price, since they don't want to make any deal that looks unfavorable compared to what they could get today. From a theoretical point, under the efficient market hypothesis, the future price at time t can be interpreted as the market best estimate of the future price at maturity, which we write as below equation. This equation tells us that, on average, futures should convert to the actual spot price when the contract expired. Now we come to our research question and data processing challenge we face. Ideally, we want to verify whether those lead-lag relationships really hold. That motivates my main question: can we find quantitative evidence of an efficient market hypothesis in the future spot market? Well, some researchers did similar study in this topic. Cavella in 1987 used F-test on 3-stage least square on SP 500 spot and future price find futures lead spot. Jacqueline and Dell found by causality in Lin Hong Pork Belly in Indian markets by using Granger causality. Zhang and Liu found by directional causality in CME natural gas as well by using linear and nonlinear Granger causality test. Now, I want to flag 2 key data challenges in this research. First, raw data prices are both non-stationary and autocorrelated. Non-stationarity means the level and variance of price can drift over time, so comparing different periods directly isn't valid. A stationarized data allows to make our samples comparable when we're doing data analysis job. Autocorrelation means today's price change depends on yesterday's or more yesterday's, so our observations are not independent. If we ignore that, our statistical test will be biased. Even after making the series stationarized, some autocorrelation often remains, so we need method to exclude it or adjust for it. Second is the varying forecasting horizon issue. This is a common issue for financing data like future option bonds. I just want to mention here, but it is a nature of this kind of data. It's hard to correct it. When we say future price at time t and time t plus 1, both refer to the same contract's maturity at fixed 1 day. As time t moves forward, the time to maturity date shrinks. So we are effectively observing the same contract at different horizon, not 2 different contracts. This research I will focus on addressing the issue of seasonality and autocorrelation of price data. Let's see how other researchers process the data in this question. First one, on study SP 500 by Cavella in 1987, the researcher used raw data on first order difference, which is today price minus yesterday price, and then declaring data as stationary without any formal unit root test or stationarity test support. So even if I believe they say data is stationary, but they ignore the problem of autocorrelation, which could lead the result unreliable. Secondly, research by Jacqueline and Dell in 2011 studying Indian market Lin Hong and pork bellies. They chose to use raw data without any processing, which is good, but hard to believe the raw data passed the ADF and the PP test in stationarity. I was concerned this stationarity result is false negative due to low test power, and again, they ignore the problem from data autocorrelation. Last research by Zhang Liu in 2011 studying natural gas from CME, they use log transform price to staticize the data. Once again, they ignore the problem from autocorrelation, and more importantly, use log data will lose or discount information in future and spot price. So for this question, it's not ideally method for doing data transformation fix the non-stationarity problem. Therefore, as we saw so many pioneers work, we could conclude the key limitation in data processing in following points. First, it is better to use raw data than transform data like log return, log difference will weak or lose significant price movement signal in two markets. Secondly, we could find the big issue. Most researchers ignore the problem from data autocorrelation. They only care about data stationarity. That makes me to consider, in order to answer this question, I need to think about how can I preserve the maximum information in raw future spot data to accurately uncover lead-lag relationships between future and spot markets. In short term, I want to use raw data, fix the problem of stationarity and autocorrelation. Well, there are some methods and tools might be helpful. For stationarity problem, inspired by Pharma's efficient market hypothesis, I will stationize the data by the form of today's future price minus spot price and compare the relationships of the expectation of today's spot price minus some day's spot price. The blue table is one example of autocorrelation function checked for live-hung price data, which I will present in later analysis. As we can see, the raw data in left two plots are highly correlated, but after I apply the method in substitution in right two plots, the stationarity of data is getting better. Bottom right plots are price series overview. For autocorrelation problem, some methods on linear dependence measure to test the lead-log relationships are helpful. Cliff suggests could fix the problem of autocorrelation by adjusting the degree of freedom in statistical test, and it is based on sample variance estimator. Specifically, in Pearson correlation could use a modified statistical test to accurately identify cross correlation without disturbing from data itself. By applying t-test, but not on degree of freedom in n-2, instead we'll use degree of freedom corrected from sample variance estimator, which could allow us fix the problem of autocorrelation. For more rigorous, I will also consider use surrogate test for random surrogate 500 or even more to 1000 just to destroy the linear coupling of data. Last step, for more rigorous as well, I will apply Buffoni correction for finally p-value result just to control the family-wise error in this lead-lag relationships question. Second, for Granger causality, same thing to use the modified f-test version from Cliff, which he adjusted the degree of freedom in f-test based on the variance estimator of sample's residual vectors. Then again, we'll apply surrogate test and the Buffoni correction for the same purpose. For nonlinear dependence measure, I will use mutual information. The dynamic correlation exclusion, which provided in my supervisor Joe's GIDT toolkit, could be helpful in adjusting data autocorrelation problem. This method by doing dynamically exclusive data near the target data. For the specific value in exclusive, I will refer to the autocorrelation function in each case. And the surrogate test, Buffoni correction, will be applied as well for the same purpose in linear case. Let me introduce the data we will analyze in this research. The first one is live-hung future and spot price from Dalian Commodity Exchange. The overview of data series is in the left, where red line is the spot price and the blue line is the future price, including price information from future contracts LH2405 to LH2505. So this is the from 2 months rolling future price, which only contain price will be expired in next 2 months. The data period covering from 2023 November 20 to 2025 March 20. Data length is 322, which is quite short. Left side are two autocorrelation check functions for both future and spot raw data. Again, could see data highly autocorrelated. The second dataset are Henry Hub natural gas future spot price from Chicago Mercantile Exchange. Data is being divided into 2 periods. The first period is from 1997 January 7 to 2008 December 29. Total length is 2,480. The second period is from 2007 January 2nd to 2019 February 22. Total length is 2303. The raw data overview is in table. Column 1 is a spot price. Column 225 is a future price from contract 1 to contract 4, whereas contract 1 meaning front month contract, which will be delivered in the next calendar month, and the contract 4 is the forthcoming month. Check the autocorrelation function for period 1 data could say data are highly correlated. The first crossing zero in autocorrelation function is t equals 700, and this is more than 2 years. Same issue in period 2 data, and for some data the first crossing zero point even up to 900. We really need to take this issue seriously. Now I will start to analyze the dataset. The method I will apply first is Pearson correlation and mutual information for both linear and nonlinear dependence measure. I will cover both results together since those are common measures for linear versus nonlinear relationships. For linear measure, Pearson correlation will focus on 2 questions. First, is future price leads spot price linearly? This will be measured by adding time embedding tau in spot price, then compare first time series, the ft minus st with the different time series changed by time embedding. The second question is other direction, is spot price leads future price linearly? Similarly, by measure the relationship between the fixed series ft minus st with changing series, but here I will pick the tau as negative value to see if past the spot price bring any information to today's future price linearly. For nonlinear perspective, question is same in linear slides. Is future price leads spot price, and is spot price leads future price? The time series being measured is the same as in the linear, just here we use mutual information to detect the nonlinearity in the relationships. First, I will demonstrate result in live hung future and spot price. Those are results of live hung future and the spot price. In here, I checked for time delay tau from negative 66 to positive 66 trading days. Therefore, our fully corrected should be 0.05 divided by 133 if we choose 0.05 as a significant value. For p-value smaller than this point, could consider as a significant value, which is targeted by read point in the plot. The time embedding there checks the 2 directions. Therefore, for negative tau, if the results are significant, meaning spot price leads future price linearly or nonlinearly. For tau positive, if results are significant, meaning future price leads spot price linearly or nonlinearly. From the results showing in table, we could say future leads spot price in the short term in linearly. However, for perspective of mutual information, we find the future leads spot price in the longer term. The significant value remains at around 14 trading days, which is about 2 months and covering the whole contract period. Moreover, I observed the apparent rise and subsequent fall in non-significant Pearson correlation at very small tau in negative side and very large tau in positive sides, likely reflect stronger autocorrelation caused by the reducing effective sample size at those legs. Like the autocorrelation checked on the right bottom, we could say as increasing in tau, the autocorrelation is increasing due to shorter data in the sample size. By zooming in the scatter plot of the points where Pearson correlation and mutual information reach the maximal value, as well as the result is significant, I could observe the relationships in the dataset. For maximal raw value in Pearson is 0.535 when tau is at plus 10 days, result as shown in left column of the table. We could observe the strong linear relationships, whereas for mutual information, in the right column, maximum value is 1.65 nets in tau equal to plus 24 days. I colored the data by day to expire, and we could observe the price divergence for data away to the expiry day. Next part, I will demonstrate the result for Henry Hub natural gas future and spot price. In this presentation, I will only present one example, which is the spot price with the future contract 1 in period 1. Again, I did a similar job as in the leaf hung data, results are showing in the table whereas rate points as significant value. I checked the tau from negative 66 to positive 66. For natural gas, we observed the bicausality in both Pearson and mutual information results, which is different from what we saw in the leaf hung data. The results from spot to future are slightly stronger than future to spot. Especially in mutual information, we could observe that in right plot, the negative tau sides are kept significant even to the negative 66 day. However, for natural gas seems more reliant on future price in short term by showing larger value in both Pearson and mutual information at tau equals to 1 and 2. Similarly, I checked the scatter plot of the points where absolute value of Pearson correlation and mutual information reach their maximal value, as well as the result is significant. The maximal absolute Pearson correlation is 0.42 at tau equals to negative 7, and for mutual information, the maximal value is 0.293 nets, happened at tau equals to 1. By colored the points on the day to expiry date, we do observe the same price convergence as dates closer to expiry date. Last part, I checked the Granger causality, which is the most popular for this type of question. My question will focus on is the future price Granger cause the spot price, and is the spot price Granger cause the future price. I will use ARMA 11 model to analyze the two datasets. For Granger causality, I will just apply the raw data since the stationarized form here is hard to interpret. Additionally, time embedding tau is considered here to adjust the log lead of the two price series. This is the result for leaf hung data. Here I check the tau from 1 to 16 trading days. Left plots as result for future Granger causality spot, whereas the right plot are spot Granger causality future. Only a few data are significant after performing correction. Future Granger causality spots in shorter term, whereas spot Granger cause the future in the longer term. Results are slightly different compared with what we find in Pearson and mutual information, which only has causal relationships from future price to in the short term. Here we could say in the left plot, future do has a Granger causality to spot price in short term, but we could find Granger causality in ARMA 11 model also captures some longer significant relationships from spot to future, which is around 60 trading days. This is one example result for natural gas spot price with the natural gas future contract 1 in period 1. We check the top from 1 to 16 trading days. Left plot is a future to spot, whereas the right plot is a spot to future. The result with the rate means significant. So as you can see, this again is a bi-causality case. However, future price seems leads spot price are stronger than the spot price to future price, especially in the short time term, but spot price leads the future in the longer term by showing the rising in the significance of a f-test value in the right plot. Actually, this find is similar to what we found in Pearson and mutual information, but granular causality seems emphasize this likely relationships and capture the relationships for the longer time delay. Now come to the final part of the presentation, the conclusion. In this research, I studied the leg-lag relationship between future and spot price to detect farmers' efficient market hypothesis. Because I don't want to lose any significant movements on the price changing in the two markets, I choose to apply raw data which could preserve the whole information. But this makes me to meet the most fundamental and the biggest challenge in data pre-processing works, non-stationarity and high autocorrelation. To fix this issue, I applied the stationarity form, which inspired in the pharmaceutical relationship of future and spot price. For autocorrelation problem, I used the modified statistical test in degree of freedom for linear measure, Pearson, and the granular causality. Use dynamic correlation exclusive for nonlinear measure, mutual information. The surrogates and biphonic correction on the final p-value to ensure my results are reliable. For the finding, we do find the evidence of efficient market hypothesis on both data, since those measures do detect the significant relationship between future and the spot. And we also find bi-causality, but it is in different time lengths. For methodological innovation, this research filling the gap of previous studies that ignore the issue of autocorrelation and providing a more rigorous method for empirical testing of the efficiency of future and spot markets. For future work, including expand to multi-product and cross-market analysis. In addition, further optimize the statistical method to approaching perfect accurate could help people knowing and approaching to the true side of the market, or this word from perspective of data, and knowing the relationship between two markets is crucial for regulator, especially in monitoring market movements. Therefore, could help them to detect the earlier signal for abnormal price fluctuations, so that could protect the market health investing environment. This is the end of my capstone research presentation. Thank you for listening.